Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Sum of two integers, Leetcode 371. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given two integers a and b, and we have to return the sum of two integers without using the operators plus and minus. For example, here a is equal to 1 and b is equal to 2, so our output should be 3. But we shouldn't use addition and subtraction operators. Similarly, in example 2, a is equal to 2 and b is equal to 3, and we should get the sum equal to 5. Now in terms of solution, when faced with a question, perform arithmetic operation without using the arithmetic operator, the chances are that we will have to use bit manipulation. The key insight is to realize that basic mathematical rules still apply when working with the numbers in binary representation. In the current problem, the focus is on performing addition. So let's see how addition works at the bit level. Let's take a equal to 7 and b equal to 5. Now 7 in binary is 111 and 5 is 101. Now when we add these numbers at the bit level, starting from the 0th position, we will add 1 plus 1, which will give us 2, which is 10 in binary. So we will write down 0 here and carry forward 1 to the next bit position. Now at bit position 1, 1 plus 0 is 1, plus we add carry from the previous position. So 1 plus 1 is equal to 2, which is 10 in binary. So we again write down 0 and carry forward 1 to the next bit position. And now at bit position 2, we add the bits 1 plus 1, which will give 2, plus we add the carry from the previous position, which will give us 3, which is 1 in binary. So we will write down 1 and carry forward 1 to the next bit position. And finally, at the last position, there are no more bits in the number, but we have 1 carry, so we write down 1. Hence, after performing the binary addition bit by bit, we arrive at the result 1100, which is 12 in decimal. Now when adding two bits, we observe that if both the bits are 1, like here, the result at that position is 0 and we carry forward 1 to the next position. Similarly, if either of the bits is 1 and another one is 0, like this one or this one, the result at the position is 1. And finally, if both the bits are 0, the result at that position is 0. And which operator can do this? And the answer is XOR or exclusive OR operator, because XOR operator returns 1 if the bits are different, but 0 if the bits are same. So now let's XOR the numbers 7 and 5. So 1 XOR 1 will be 0, 1 XOR 0 will be 1, and 1 XOR 1 will be 0, which is 2 in decimal. But sum of 5 and 7 is 12 and not 2. And the reason we get the partial sum is because we still need to account for the carry, which occurs whenever two ones are added at the same bit position. So how can we calculate the carry? The carry is generated when both the bits at the given position are set. But if either of the bits is not set, we get 1 in output but 0 in carry. Or if both the bits are 0, we get 0 in both output and carry. So we get the carry only when both the bits are set. And which bitwise operator can do that? And the answer is bitwise AND operator, because it outputs 1 only when both the input bits are 1. So now let's perform bitwise AND between 7 and 5. So 1 and 1 will be 1, 1 and 0 will be 0, and 1 and 1 will be 1 again. So we get 5 in decimal. But the carry should be added to the left bit of the one which generated it. For example, when we produce the carry here, we added it to the next bit in the number. And to achieve this, we can left shift the carry by 1. This ensures the carry contributes to the correct higher position in the sum, aligning the bit positions correctly. For example, here if we left shift 101 by 1, we will get 1010. And now to add these numbers, we can't use addition. We have to use combination of XOR and bitwise AND. And now when we XOR these numbers, we will get 0001 from right to left, which is 8 in decimal, which is still not equal to 12. And the reason for this is because we still have a carry at bit position 1. So XORing the numbers results in the partial sum, and using the shifted carry completes the sum. So we need to repeat this carry propagation till the carry becomes 0. So continuing with our next iteration, again we generate the carry by taking the AND between the two numbers and left shifting it by 1. So bitwise AND between these two numbers from right to left will be 0, 1, 0, 0, which when left shifted results in 0, 1, 0, 0. And again we perform the bitwise OR to add this carry, which will give us the result as 1, 1, 0, 0. And now when we perform the AND operation between these two numbers, the carry will be 0. So now the process stops and finally we will get the result as 1, 1, 0, 0, which is 12 in decimal. So the key insight here is that the XOR operation gives the partial sum and the combination of bitwise AND operation with left shift operation gives the carry, and repeating these steps until the carry becomes 0 results in the sum of the two numbers. Here is a quick code walkthrough of the algorithm we just talked about with Java code on the left and Python on right. We can implement this algorithm using either a recursive approach or an iterative approach. Here we will solve it using iterative approach as it avoids recursive overhead and it's more memory efficient. If you are interested in the recursive approach, please check the code link in the description below. However, the logic remains largely the same except the recursive version uses function calls instead of a loop. Now we will initialize a loop that continues until the carry becomes 0 and we will be storing the carry in variable b. Now let's calculate the carry bits using bitwise AND of a and b, and we calculate it before performing bitwise OR of a and b because that overrides the original value of a. Now let's calculate the partial sum by performing bitwise OR of a and b and storing it in a. Also, let's left shift carry bits by 1 and store it in b, which we can XOR with a in the next iteration. And we continue this process until the carry becomes 0. And in the end, we will return the final sum which we have stored in variable a as our answer. Now the time complexity of this approach is O of n, where n is the number of bits in the larger of the two numbers. This is because in each iteration, at least one higher order bit of b becomes 0. And in the worst case, it takes O of n iterations to reduce b to 0. And for the 32-bit integers, this reduces to O of 32 equal to O of 1. And in terms of space complexity, it will be O of 1 since no additional space is required apart from some constant variables like a, b and carry used during the computation. However, the space complexity for recursive approach will be O of n as each recursive call consumes stack space. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.